used to doing this, to making it so brief. But state function, I was really kind of surprised. We'll be dealing more with state functions as an important concept in chemistry. It just means that only the initial and the final state are what counts. They don't care what happens in between, so that's what we call path independent. Exothermic, physical phase change, that releases energy. You see your options there. For C, the fact that this is a negative enthalpy means it's actually exothermic. For D, of course, gases have the greatest amount of kinetic energy. For E, vaporization is what we're doing when, let's see, which vaporization or condensation are we breaking intermolecular bonds? Of course, that's going from a liquid to a gas, vaporization. For F, standard conditions for thermodynamic problems are 25 degrees Celsius, 1 bar or 1 atmosphere pressure. And I need to see both of those. For G, isolated or closed system basically means, I took a variety here. These were each worth 1 point. Try to talk fast, talk too fast. Each worth 1 point, and if you just kind of almost got this idea, I gave it to you. So you see down in my answer key for H, I did a fair bit of kind of ciphering, but basically the one with the higher specific heat, which is aluminum, requires more energy. All right, so for A, then these were all kind of small things here. I think they were 3 points apiece. The first one is basically take that, the heat of vaporization given in joules per gram and convert it to kilojoules per mole using the molar mass of the compound. For B, you're supposed to use Q is equal to MC sub P delta T. In this case, you knew Q, you knew M, you knew delta T, but didn't know C sub P, basically. For C, this was one of those change in internal energy problems. Remember, it's equal to Q plus W. Here you had to kind of decide what the sign of Q and W were. The sign of Q is positive, the sign of W is negative, so when you add them together you get negative 171. Down here for D, this last one, given this, notice I put a 1 here, kind of this is like, this is our puzzle piece here. Given this information, we know this heat of reaction. What is the heat of the reaction of formation? So this is the standard molar enthalpy of formation, basically, of NO2. So the equation of interest is right here. What are we trying to get to? Basically, we're trying to form 1 mole of NO2, 1 mole of N2O from N2 and O2 in their standard states under standard conditions. So you need 1 mole of N2 and a half mole of O2. So actually, this equation of interest is related to the puzzle piece that we're given by actually reversing it and taking it times a half. So you end up with basically that negative 163.2 times a half times negative 1. So that was that one. On to the next one. Let's see. Yeah, so this one you were given a volume of a liquid, given the density of the liquid. And of course, we can get to the molar mass of the liquid. Using all of those, basically go from that volume to the amount of energy that's released, and specifically using that volume of methanol. So that's kind of that one. This one, yep. This one, it was using this approach. I don't know what else to say about it. So one of the things I noticed, sometimes students don't show their work very well. But the other thing is, remember that the little a and the little b are actually the stoichiometric coefficients in the balanced chemical equation. So, and then on the next page, oh, Hess's law. So when I did this for my answer key, actually notice what I did. I looked at my puzzle pieces 1, 2, and 3. Actually focused. I skipped 1 and I went right to 2. For me anyway, and under 2 I put the squiggle mark what I was focusing on. So I focused on the NO2 and made that work by reversing it, taking it times 1/2, so etc. And anyway, you can kind of see down here how I manipulated each of the equations. So worked. And then this one was kind of like what you did for your lab. you guys did ammonium chloride, but this is sodium hydroxide. This is exothermic instead of endothermic. So basically, you have two things going on in your beaker. You have what I call the Q of the solution. The solution in this case is going to heat up, and the Q of the reaction. The reaction actually is the dissolving process. So if it's isolated, that is equal to 0. So actually, some of your work, I'm still not seeing this kind of important kind of layout of how you approach the problem. But we can see actually how much the change in thermal energy of the solution by taking the mass of the whole solution, not just the water, but the water and the NaOH, times the specific heat of the solution. They said go ahead and use it for the same as the water, delta T, converting it into kilojoules. This is the last term. So then once you find the change in thermal energy of the solution, that is equal to negative change in thermal energy of the reaction, which in this case is the dissolving process. So one last thing is we're supposed to normalize it based upon the mass of the salt that was dissolved. So that's the energy divided by the mass, or the amount of salt that was dissolved. We're supposed to go for moles. So you can start with grams and then convert it to moles using the molar mass of NaOH. Don't you love the molar mass of NaOH? It's like 40.00. If you're like me, you're like, is that right? Yep. So that's one. In general chemistry, we do a lot with sodium hydroxide, and you're like, oh, I love the molar mass of sodium hydroxide, almost as much as the molar mass of magnesium oxide or magnesium. So this last one, actually we had three things going on. You had a certain amount of steam. I just put the letter G here for steam because it's in its gas state. A certain amount of energy was released as that condensed, and then that condensate needed to cool, and then actually kind of your body of water, which is 475 grams of water, it will actually heat up, and it will meet a common temperature. So that's kind of the approach I did for that one. So notice in this case, if it's isolated, that those three terms added together equal 0. And so the thing that you don't know is the heat of condensation, the delta HCOND. So we know the mass of the condensate. I noticed a lot of you guys got to the mass of the condensate by difference because it gave you the final mass of the body of water plus the steam that had condensed. So that's 12.2 grams. And anyway, you work it. Is it messy? A little bit. Okay, not too bad. But I ended up with the latent heat of condensation is equal to negative 27,600 joules per 12.2 grams, or that amount of energy per gram. And then it was supposed to be, and then we were after actually, that's the heat of condensation. We were after the heat of vaporization, which has the relationship of being equal in magnitude but opposite in sign. So then the heat of vaporization actually is positive, 2,260 joules per gram of water, excuse me. All right, so that's kind of